This is part 5 of a series on decision trees. In this video, we will take a look at the CART algorithm for classification. In the last 4 videos, we looked at ID3 algorithms for classification and regression. Starting from this video, we will be discussing the CART algorithms. In Chapter 4, we will examine the CART algorithm for classification in detail through 6 videos. And in Chapter 5, we will briefly look at the CART algorithm for regression. In this video, we will look at an overview of the CART algorithm and how to handle ordinal and nominal categorical features. Now we will briefly look at the CART algorithm. CART stands for Classification and Regression Trees. CART is one of the decision tree algorithms proposed by Leo Breiman in 1984. The most widely used decision tree algorithms are ID3 and CART. Let's compare ID3 and CART decision trees. We took a detailed look at the ID3 algorithm in the last 4 videos. The ID3 algorithm primarily uses multi-way splits, or n-way splits, for categorical features. A multi-way split creates a separate branch for every distinct value of a categorical feature. ID3 performs the multi-way split by selecting the feature with the greatest information gain, that is, the feature with the greatest entropy reduction. Important features are split first, and less important features are split later. In other words, more important features are located higher in the tree, while less important features are located lower in the tree. The ID3 algorithm is primarily suitable for classification tasks using datasets that have categorical features. On the other hand, CART is an algorithm that uses a binary tree structure to perform both classification and regression tasks. As shown on the right, each node is split into 2 branches, left and right. Each node contains a yes/no question. If the answer is yes, it goes down the left branch. Otherwise, it goes down the right branch. CART performs binary splits at every node by selecting the best split feature and best split point with the greatest information gain, that is, with the greatest entropy reduction. This is the best split feature at this node. And this is the best split point. Since the best split point is a real value, CART is suitable for handling continuous features rather than categorical features. Again, ID3 is suitable for categorical features, while CART is suitable for continuous features. CART is widely used in various domains due to its simplicity, interpretability, and effectiveness in handling nonlinear relationships between features and target variables. CART can handle categorical features as well if they are converted to numerical features. Next, let's look at categorical data. Categorical data, or qualitative data, represents features grouped into non-numerical categories, such as color or quality grade. Categorical data includes nominal and ordinal data. Nominal data has no inherent order. For example, gender and color are nominal data. On the other hand, ordinal data follows a logical sequence. For example, satisfaction level represented as low, medium, and high is ordinal data. In this dataset, the color feature is a nominal variable and is classified into one of blue, green, and red. These colors are independent of each other and have no order. So it cannot be said that one is larger or smaller than the other. The grade feature is an ordinal variable and is classified into one of high, moderate, and low. This feature have a natural, ordered ranking. We can say that moderate is slightly larger than low, and high is much larger than low. However, since this is also a categorical variable, the precise distances between categories are unknown or uneven. This is an example of creating an ID3 classification tree on this dataset. Since ID3 was originally designed to handle categorical features, there is no particular problem in creating an ID3 tree on this dataset. Next, let's create a cart classification tree on this dataset. Since cart was originally designed to handle continuous numerical features, these categories must be converted into numerical values as follows. The blue category of the color feature is encoded as the integer 0, red as 1, and green as 2. This order is arbitrary. Converting categorical variables into simple integers in this way is called label encoding. The color feature is a nominal variable, and each category is independent of each other. However, these numbers have an order. The number 2 is greater than 0, but we cannot say that the color green is greater than blue. For this reason, encoding nominal variables in this way is generally undesirable. For example, in a linear regression model, the predicted value of the target variable y can be expressed as follows. However, it doesn't make sense to calculate this function value using nominal variables with no size. The same thing happens to most machine learning models, such as support vector machines, as well as linear regression. To solve this problem, nominal variables must be one-hot encoded instead of label encoded. We will look at one-hot encoding on the next slide. However, in decision tree models, it is possible to label encode nominal variables in this way. This is because in decision tree models, variables are not used in calculations in this way, but only for splitting nodes. Therefore, this dataset can be classified as follows, using a cart decision tree. Since the grade feature is an ordinal variable with a clear rank, it can be label encoded as follows. Next, let's take a look at one-hot encoding. In most machine learning models, nominal features are one-hot encoded, as explained earlier. First, label encode the nominal variable color as follows. And then one-hot encode it as follows. The label 0 is encoded as 100. 1 is encoded as 010, and 2 is encoded as 001. Label-encoded values have ranks from 0 to 2, but one-hot encoded vectors have no rank and are independent of each other. Since the Euclidean distance between one-hot encoded vectors is square root 2, all vectors are separated by the same distance. Therefore, since these vectors are all independent, one-hot encoding is suitable for nominal variables. Using these features, we can create a cart tree as follows. We will take a detailed look at how to create a cart tree by finding the best split features and best split points in the next video. For cart decision trees, you can one-hot encode nominal variables or label encode them as in the previous slide. In this video, we looked at an overview of cart and looked at ordinal and nominal categorical variables. In the next video, we will examine information gain and the best split points, and learn how to create a cart tree using them.